Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
String theory suggests that the universe is not made of particles, but of tiny, vibrating strings of energy, harmonizing to create all reality.
Welcome to the bizarre world of quantum mechanics, where particles can be in two places at once.
Let's just jump right into this explainer, shall we? Today, we're unpacking the architecture of quantum field theory. Now, this is widely considered the most successful, rigorously tested, and yet, let's be honest, mathematically confounding theoretical framework in the history of human science. We're going way beyond the basic quantum mechanics of a single particle here. We're breaking down the complex, multi-particle field theory that modern physicists actually use to understand the fundamental forces of our reality. And look, if you find the sheer density of this topic daunting, you are absolutely not alone. I mean, even brilliant, pioneering physicists like Julian Schwinger felt the angst of just how mathematically heavy these concepts can be. Schwinger famously noted that the lack of appreciation of these facts by others was depressing, but understandable. During the intellectual explosion of the 1940s and 50s, trying to communicate the profound depth of these mathematical fields to other scientists was incredibly frustrating, mostly because the math just kept breaking down in seemingly impossible ways. But lucky for us, today we have the benefit of hindsight, structure, and decades of refinement.
So, here's our agenda for today's explainer. First, history and theoretical background. Second, inside the standard model. Third, principles of Feynman diagrams. And finally, infinities and renormalization. Let's get right to it.
Section 1. History and Theoretical Background. Tracing the Evolution of QFT.
You see, the foundation of this field was born out of absolute necessity. Physicists realized pretty quickly that early quantum mechanics just couldn't adequately handle particles moving near the speed of light, nor could it explain how particles are actually created or destroyed. And this led to a monumental leap, quantum electrodynamics, or QED, which successfully married special relativity with quantum mechanics. From that initial triumph, physicists spent decades unifying more forces, culminating in the standard model we rely on today. But the application of QFT didn't just stop at high-energy particle colliders. Today, the exact same mathematical frameworks are used in condensed matter physics to explain the behavior of countless interacting electrons in solids. This gives us the theoretical basis to understand mind-bending phenomena like superconductivity and complex quasi-particles.
Moving on to Section 2, Inside the Standard Model. The universe's fundamental building blocks. We aren't just dealing with a random soup of matter here. The universe is actually incredibly organized. Think of the fermions, that's your 6 types of quarks and 6 types of leptons, as the rigid scaffolding of matter. They make up the actual physical stuff of the universe. But scaffolding alone doesn't really do anything without forces acting upon it, right? And that is exactly where the 4 types of gauge bosons come in. They're the dynamic communicators, zipping between fermions to carry fundamental interactions, like electromagnetism or the strong nuclear force. And finally, all of these particles are wading through the cosmic molasses of the Higgs field, interacting with the Higgs boson, which serves the absolutely vital role of endowing these elementary particles with their distinct masses.
Now, the interactions between these particles are governed by something far more complex than simple magnetism. Back in 1954, Chen-Ning Yang and Robert Mills expanded on early quantum electrodynamics to create Yang-Mills theory. They generalized local symmetry, leading to what physicists call non-abelian gauge theories, and this was a massive, radical departure from earlier physics. Think about it. In an abelian theory like QED, the force carrier, the photon, has no electrical charge of its own. It literally just carries the message. But in a non-abelian theory, the particles interact by exchanging massless gauge bosons that themselves carry a type of charge. Because the force carriers are charged, they actually interact with each other. This creates a beautifully complex, highly dynamic, and incredibly difficult mathematical web that perfectly describes forces like the strong interaction binding quarks together.
All right, Section 3, Principles of Feynman Diagrams, Visualizing Particle Interactions.
Because we can't literally see these subatomic interactions with our own eyes, we use Feynman diagrams. But it's super important to understand that Richard Feynman didn't just draw these as simple, pretty illustrations for his presentations. When he debuted them at the Pocono Conference back in 1948, they actually confused the older generation of physicists, like Niels Bohr, who completely thought Feynman was abandoning quantum principles for classical particle trajectories. But Feynman was doing something genius here. He was creating a highly rigorous bookkeeping device. The lines connecting different vertices represent the propagation of virtual particles through space and time. But every single line and vertex directly corresponds to a highly specific, extremely convoluted mathematical integral. So these diagrams, they are literally equations disguised as pictures.
So, the really crucial point is understanding the difference between the two main types of these calculations. On the left, we've got simple tree-level diagrams. These are entirely devoid of loops and describe the lowest order, most basic interaction processes between particles. But as we know, reality is rarely that simple. The quantum vacuum is constantly bubbling. Particles are continuously emitting and reabsorbing virtual particles as they travel. So to make the math actually match reality, we have to calculate the n-loop diagrams you see on the right. As the name suggests, they contain loops and map out higher-order interactions, known as radiative corrections. Without calculating these loops, our predictions just wouldn't match the extreme precision we see in physical experiments today.
But this creates a massive plot hole in our physics story. What actually happens when a naive computation of these complex loop diagrams results in divergent momentum integrals? In plain terms, when physicists in the late 1940s first tried to calculate the math for these higher-order loops, they hit a severe crisis. Almost all the terms in their perturbative expansions resulted in infinity. And in physics, an answer of infinity usually means your theory is predicting total nonsense. The math completely broke down, and honestly, it threatened to destroy quantum field theory entirely.
Which brings us to Section 4, Infinities and Renormalization, Fixing the Infinite Calculations.
The solution to this nightmare was renormalization. Developed as a highly rigorous mathematical process, it's specifically designed to remove those seemingly impossible infinities from the loop diagrams. And crucially, this is not just some mathematical trick used to sweep infinity under the rug. It was a profound physical realization that parameters we usually think of as constants, like a particle's charge or mass, well, they aren't actually static. They're running coupling constants that actually change depending on the energy scale or the distance at which you measure them. By carefully redefining these quantities based on a known energy scale, physicists could absorb the infinities and make the theory yield finite predictions of unprecedented precision. It's truly brilliant.
However, even with the absolute incredible success of renormalization, quantum field theory is definitely not a finished book. There is a massive frontier of physics beyond the standard model. Current QFT simply cannot account for huge pieces of our universe's puzzle, like dark matter or the principles of supersymmetry. But the biggest, most glaring hole is quantum gravity. You see, when physicists try to incorporate the force of gravity into quantum field theory by introducing a particle called the graviton, the math just shatters. Because the graviton has a spin of 2, its coupling constant has negative mass dimensions, and this leads to non-renormalizable infinities. Basically, you would need an infinite number of counterterms just to fix the math, which means the theory completely loses all of its predictive power.
Which leaves us with one final, incredibly exciting question to ponder. What happens when quantum field theory finally meets string theory or quantum gravity? What entirely new mathematical frameworks are going to have to be invented when our current models are forced to explain the darkest, most massive mysteries of our universe? Will quantum field theory evolve into something completely unrecognizable, or will it be replaced by a framework that is even more profound? That, my friends, is the bleeding edge of modern physics.
String theory suggests that the universe is not made of particles, but of tiny, vibrating strings of energy, harmonizing to create all reality.
Welcome to the bizarre world of quantum mechanics, where particles can be in two places at once.
shares.
This website makes learning so easy. I found all my resources here.
Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.